Okay, so we are back, and we're going to take a look at estimating a population mean. We're kind of done with proportions. Now we're going to talk about means. Remember, means are when your data is numbers, right? So you can have an average of them. So my data might be 22, 27, 23, 32, 31, and you take an average of them, and you can end up with a sample mean. You can use that sample mean to estimate what the population mean would be. Say I wanted to know the average age of all community college students. Then I might take a sample of community college students, and that would give me a sample mean, X bar. That would be my best point estimate for what the real population mean would be of all college students. So again, whoa, what just happened here? That was strange. Um, Sorry, this is a little bit disturbing for me. So again, we take a sample, and from that sample we can find a sample mean. And that sample mean would be our best guess for the population mean. So our sample mean, X bar, is what we would guess at to end up with our population mean, mu. This is going to be a parameter, because it's the population's mean, like all community college students. And this is our statistic because it's for a sample, what we got in our sample. Our sample ended up with statistic, with a sample mean of our sample, which is our best, again, that's our best point estimate, our best guess of what the population mean would be for all community college students. We're also going to take a look at making confidence interval, because again, that X bar, that one best guess, is just one number, and you really should take from that X bar, you really should take a sample, right? Take a little interval. So you again do so many standard deviations this way, so many standard deviations that way, to end up with a lower limit here and an upper limit there, and say that it's between this spot and that spot, really. And that would be your confidence interval that you're kind of looking at. So that's what we're going to do again, only with means instead of proportions. And then also, again, be able to find the sample size to stay within a certain error. So here are some numbers things you need to know. Again, mu naught or mu. A lot of times we just call it mu, honestly. So it might just be mu. That's our population mean. X bar, you guys know, is our sample mean. Sigma, that's our population standard deviation. N is the number of numbers we have, number of our sample size. E is our margin of error. And then Z alpha over 2, which is what your book will call it, but really here in class we're just going to call it our critical value. That's the same thing as the Z-score, that says how many standard deviations we want to be away from the mean. So that's our critical value, how many standard deviations we're going to go to the left and to the right of the mean. So go ahead and write those down. Pause this if you need to write those down or anything in your notes. Okay, and then just a reminder again, the confidence interval is our statistic. In this case, our statistic is going to be our X bar, our sample mean, plus or minus our critical value, multiplied by our standard deviation, whatever, how many number of standard deviations we want to go. And for here, standard deviation is going to be S over square root X, sorry, mu, it's going to be sigma over, oh, this pen is weird, sigma over square root of n. So if you kind of remember from central limit theorem, standard deviation of a sample, right? Because we have X bar, it's going to be sigma X bar, which is sigma over square root of n. If you guys remember that, you remember for central limit theorem, sigma X bar, sigma for a sample mean is sigma over square root of n. That's where this guy comes from, sigma X bar. All right, so that is what we're going to do with this for means. And this is just me reminding you about the fact that for a sample, right, then your standard deviation is going to be a lot smaller. It's going to be sigma x bar, sigma over square root of n, because here this red curve is just a single game. If you take a compilation of all games, just all single games, this would be the distribution. So, if you randomly picked a game, unusual might be, this might be a couple standard deviations. Oops. Let me redo that. This might be a couple standard deviations here, right? But if you take a sample of 25 games and average them, you take every possible combination of 25 games and average those 25 games, this would represent all possible, kind of the mean of means, right? All possible means of 25, and then you're going to get a much smaller standard deviation because they're all going to kind of come right in here if you take 25 games and average them. So again, that whole idea that the new standard deviation, sigma x bar, is really going to be your old standard deviation divided by square root of n. Okay. Great. So this is your confidence interval. It's what we expect. It's your x bar minus your error to your x bar plus your error. In other words, it's your x bar plus or minus your error. So you can either write it the kind of the usual way that we'd seen before, where you take x bar, subtract your error, and x bar plus your error, and those are your lower limits and your upper limits. And then inside is what you're trying to guess at, your population mean. It's not x bar that's in there. I know what my sample mean is. I'm trying to guess what the population average would be. So in other words, I take a sample of college students, I end up with an average age of my sample, an x bar sample mean, and from that I'm going to guess at what all college students' ages would be, what the average of all college students would be, and that's my mu. This is for the whole population. That I don't know, right? That's what I'm trying to estimate. So that's why I took a sample, so I can estimate what the whole population would be. And you can also, again, write it this way, where you have your x bar minus e, comma, your x bar plus e in parentheses, this being your lower limit and your upper limit. So that totally works. And again, the error is slightly different than for a proportion. It's your critical value, and the standard deviation is sigma over square root of n. So it's a little bit easier, actually, honestly. All right, so this is just kind of showing you what I'm talking about here. Here's my mean in the middle that I'm trying to guess. So my mean is going to be somewhere along this range from here to here. I don't know where, but I think my mean is somewhere in here. It may not be, but I think it is, because this is where my x bar is, and I've gone 2 standard deviations this way, or not 1.96 standard deviations this way, and 1.96 standard deviations this way. Maybe I'll just do the error instead. That might be easier. I've gone 1 error this way and 1 error that way. An error being, for 95% confidence interval, 1.96 times sigma over square root of n. So 1.96 standard deviations this way, 1.96 standard deviations that way for a 95% confidence interval. All right, so you guys pause this and do lab problem 5. Find the critical value, in other words, z alpha over 2, for the 99% confidence interval. And again, that's just from the table we did earlier. And go ahead and round that to 2 decimal places. So go ahead and look that up from the table from earlier and pause this. Okay, you should be back. And again, from that table, you can take a look at it if you want. It's up. Where is it? It's up here, right? 95% confidence interval, Did I say 99? 99% confidence interval? 99% confidence interval. It's going to be 2.575, so 2.58 is what we're looking for here. 2.58 when you round it, because let's get used to doing that since your book kind of wants you to do that for your homework, so then you'll kind of be more ready for that. Okay, so that's that one. And then let's take an example. People have died in boat and aircraft accidents because an obsolete estimate of the mean weight of men was used. In other words, the weight of men has increased. It's not what it used to be. So if we base our weights of men off of these lower weights, then boats, aircrafts, elevators can't hold what they can hold. They can't hold as many people as they think they can. They become dangerously overloaded. So what we want to do is, using the weights of men from a random sample, we want to estimate what the real mean weight is of men today. So our sample ended up with N of 40. We surveyed 40 people. They had a mean of 172.55 and a standard deviation of 26. So let's try to figure out what today's true mean of all men. My sample was 172.55, but I want to know what it would be for all men. So we're going to first find our error, right? So our error is equal to our critical value times sigma over square root of n, and that's going to be my critical value for let's do a 95%. Let me check and see what it says here. Yep, 95% confidence interval. So first find the best point estimate, the best one number guess for the weight of all men. So what do you think the weight of all men today is? Well, take a look at our thing. What do you think the weight of all men today would be? The best guess at the average weight of all men. The average weight. Well, our sample says 172.55. That's our best guess, right? That's good. But we took a sample to come up with a good guess. So our best guess is going to be 172.55. And then construct a 95% confidence interval. Okay, so here I need to find my error, and that's again going to be my critical value times my sigma over square root of n. In this case, my critical value, 95% confidence interval, 1.96 times my standard deviation, which they said was 26, over square root of n, which I think was 40, right? Okay, so everybody take a minute and calculate what those numbers are. And again, I would start from the inside out, inside. So I'd start with the square root of 40 first, and then you take 26 and divide by that number. Okay, so when you calculate all that out, you should end up with 8.057, 8.06. All right, so then we're going to take a look at, oh, this didn't, oh, because I haven't set it up yet, darn it. Give me a second here. Fill that with right. And okay, try that again. There we go, much better. Okay, so again, our confidence interval is going to be x bar plus or minus our error. So in this case, it's going to be my x bar 172 point plus or minus 8.06. So I've got parentheses 172.55 minus 8.06, comma 172.55 plus 8.06. So that will give me 164.49 to 180.61. So that's my upper and lower limit. So that would be my confidence interval. That's B. And then what do the results suggest about the mean weight? Well, the mean weight, 166.3, that is in this range. But, you know, honestly, if I'm looking at safety and thinking about safety, do I really want to go more towards the lower end? I really would rather be more hedged towards the higher end to kind of, you know, hedge my bets, because you screw up that and all sorts of bad things happen, right? You kind of want to pick a number closer to the higher end just to make sure you're covered in case, you know, in case you're off. I'd rather be too high than too low if we're talking about passenger safety. Okay, so that's that one. They here it is prettier. If you want to take a look at that, you can always pause this video here and take a look at this if you want the prettier screen. And here's the C. Again, you can always pause this video now if you want to look at the prettier screen and read this kind of nice explanation that they've given. Okay. All right, so we're going to go ahead and move on and talk about your worksheet problem 6. A large department store found that it averages 362 customers per hour. Assume that standard deviation is 29.6 and a random sample of 40 hours was used to determine the average. Find the 99% confidence interval of the population mean. I want you guys to take 3 minutes, pause this video, and try to find these 8 items. Take a look and try to find these 8 items. Maybe pause it for a minute and a half and try to find out what you can, and then we'll talk about some things. So go ahead and pause it now and come back in a minute and a half. Okay, so what I want you guys to think about is, as you read through this, really try to think about, you know, what your sigma is, standard deviation. That kind of they should kind of give you. Think about your confidence level. They should give you that as well. That will tell you what your alpha is from that. And this is just alpha divided by 2, whatever you get here divided by 2. And those should also tell you what your critical value should end up being. That's something you can kind of find. And then sort of think about, if you're thinking about n and x, n is your sample size. So find sample of, or something like that, right? That's your n. And then think about what it is that varies in this problem. And that'll give you some other hints. So go ahead and pause this for another maybe 2 minutes until you try to figure these out, and you know, don't spend a little bit of effort, but don't spend a crazy amount of effort. Don't spend more than like 3 minutes at the most. Okay, so go ahead and pause it again and do that and come back. All right, so let's take a look. What's our standard deviation? Let's see. Standard deviation right here. Standard deviation is 29.6. That is our sigma. So sigma is 29.6. Our confidence level. So if you look at our confidence level, 99% confidence level interval, right? So that's what they want. So that's going to be 99%. So if our confidence level is 95%, the rest of it, our alpha, is 0.01. So alpha is sort of our significance level. It's the kind of the rest of it. So typically, It's our level of what we consider unusual, right? So typically, our guideline for unusual statistics is typically what? 5%. So our alpha is usually 5%, and our confidence level is often 95%, because those would add up to 100%. So that's kind of what we normally have. So our significance level in this case is 1%, a little bit smaller. We're making things a little bit tougher. So then this would be half of that, 0.005. And then our critical value for this confidence level of 99%, critical value for this for our confidence interval would be 2.575, or we're just going to start rounding it to 2.58. And then we'll take a look at some other things here. I'm going to change this to orange. It's a little bit better. Like our n, sample of. You find your sample size, right? Sample of what? Sample of 40 hours. This is our n. Sample of. We're sampling what? We're sampling 40 hours. So that's how many we sampled. Sample size. And then what varies in this problem? So the thing that varies in this problem is what is it, or it is how much it averages. So our x bar is our mean, our average of our sample. So so here, this random sample of 40 hours was determined the average. So this average was determined from this random sample of 40 hours. So this is what we got from our sample. We found this from the random sample. That's how we determine this average. So this is our x bar, our sample mean. We sampled that. So then the question is, you might say, well, what's our mu naught then? Where'd this mu naught come into? And here's the deal with the mu naught. The mu naught is what we're trying to figure out. That's what we're trying to find. We're doing this whole thing to find our mu naught, our mu, our population mean. We're trying to estimate our population mean from our sample mean using all these other pieces. Okay, so I will let you go ahead and now find our error. And then after that, go ahead and find the confidence interval. So it's going to be, you know, I'll let you, well, I'll give you a hint. It's at x bar plus or minus the error. So I'll let you guys sort that out. So go ahead and pause this for a few minutes and go ahead and find that, and then come back to that once you've found the error and the confidence interval, and then we can proceed. So go ahead and pause now. All right, so your error, again, is your critical value times your sigma over square root of n. So that's going to be our critical value for this would be 2.58, and our sigma is 29.6 over square root of n, square root of 40. So you will get something for that. Let's go down to the next slide. I'll give it to us. So it's going to be, you should get from that 12.1. So that should be what you end up getting for your error. And then you're going to end up doing your x bar, 362 minus your error, and 362 plus your error. So you'll end up with 344.9 to 374.1. So your mean, your population mean mu, is between these two numbers, and then went ahead and rounded to 3 sig figs here. You could also have written it, if you wanted to, you could have written it as 350, the lower limit, comma, the upper limit, 374. And there you go. Perfect. So then here's our statement at the end. One can be 99% confident that the mean number of customers that the store averages is between 350 and 374 customers an hour. Great. So again, pause if you need to review this for a little bit, and if not, go ahead and move on. This is a big deal now. what we just did, this little example that we just did and worked out, the thing about it is we're trying to find methods for estimating a population mean, which means we don't know the population mean. So here's the deal. How often do we not know the population mean, and yet we know the population standard deviation? Does that seem reasonable to you? Does that seem likely? It's really not likely at all. So if we don't know our mu, which is what we're trying to find, then we don't know our sigma, standard deviation. So we don't know either one of them. So instead, if we don't know our sigma, because we don't know our mu, what do we use to estimate our mu again? Our mu is our population mean. What's our best guess for our population mean? What's our best point estimate? What's our best guess? So in other words, we want to guess at the average age of all community college students. So we take a sample of community college students, and what do we use to guess at what all community college students' average age would be? We would take our sample average, our sample mean, right? So we use our sample mean to guess at our population mean. What do you think would be the best guess for our population standard deviation then? If you guessed it would be our sample standard deviation, then you'd be correct, right? These are both standard deviations. The best guess at the population mean is a sample mean. The best guess at the population standard deviation is a sample standard deviation. Those kind of go together. Okay, so instead of using sigma, which we don't know, instead we're going to guess at it by approximating using S. So that's what I'm going to talk about in the next slide. So very, very, very often, this is the next page of your notes, very, very often we do not know what sigma is. So instead we're going to use S to estimate that. However, the thing about it is when you're using a sample standard deviation, you're going to be off by a little bit. You're not going to be perfectly accurate because it's not sigma. So instead, you need to take a little larger, critical value to kind of make up for it, because it's likely to be biased a little bit and a little smaller than it should be. So instead of using our regular z-scores for a critical value, we're going to use what we call t-scores or t-values from the t-distribution. And I guess I can tell you guys the story. It's kind of a cool story. So if you guys have ever heard of Guinness beer from Ireland, when Guinness was first becoming larger in turn of the century, I guess it's turn of the century, like a couple turns ago now, late 1800s, early 1900s, something like that. What they started doing is they started becoming, from a small brewery, they started becoming a big brewery. Everybody loved their beer. They needed to make a lot more of it. So they needed to make it really consistent, right? Because if your beer tastes different, from batch to batch, then people are going to be upset. They want things to be what they expect. So when they start having to use a whole bunch of different farms to make their barley and grow their oats and stuff like that, then they need to find ways of making things more consistent. So what they did was they hired all of these statisticians and chemists from Cambridge and Oxford to help them make their beer more consistent. And one of these statisticians, what he did was, as he was kind of looking at different rows of barley to kind of figure out, why they varied so much and everything else, and kind of what variance to expect, he was finding a much larger variance than he expected to get. He couldn't figure out why. And that's because he had a very small sample. And when you have a small sample, then things become really, really messy. And I'll kind of explain that more in just a minute. Let me first go through the basics. So here, what we're going to do is figure out what our confidence interval should be. And again, it's the same thing, x bar plus or minus RE. X bar minus RE is our lower limit. X bar plus E is our upper limit. But the difference is our error is now our critical value times, instead of sigma, I'm going to use S. So that's the difference, right? Instead of sigma, we're using S. And for our critical value, instead of using a z-score, we're going to use a t-score from the t-table instead of the z-table. Where our degrees of freedom is n-1. Degrees of freedom comes into this t-table because your sample size changes for your adjust your t-score basically. So this is, oh right, this is your error. This is just highlighting. Again, your error, it's critical value times S over square root of n instead of sigma, and your critical value is no longer based upon the z table, it's based upon the t table. So this is the time to get out your t table that you have downloaded from Canvas. If you haven't, you should go to Canvas and download it. I've got just another couple minutes in this video, and then you should have a chance to go download it and do the rest of the stuff. But you maybe try to pause this and pull that up at least. Take a quick look at it. It's in Canvas under the chapter notes. At the very bottom, the last thing is just it's called T-table is what it's called, and it's just a file. You click on that, you should be able to download it from there. All right, so if you take a look at that T-table, you'll see across the top, you'll see confidence intervals, and you'll see another row that says one-tailed alpha and two-tailed alpha. And then you'll see these columns along the left side where it says degrees of freedom. It'll be 1, 2, 3, 4, 5, all the way up to infinity. So what you want to do is figure out, we're looking at confidence intervals. So for example, we're going to use this row and say we want a 95% confidence interval. So we're going to slide across there until we get to this one, and that's the column we're going to use. So here, this row tells me which column should I use. I want a 95% confidence interval, so I'm going to look down this column here, and say my degrees of freedom, my sample size is, say, 22. Degrees of freedom is n minus 1. Degrees of freedom equals n minus 1. You need to know that. Absolutely need to know that. It's really important, n minus 1. So if my sample size is 22, then my degrees of freedom is 22 minus 1, or 21. So my degrees of freedom is 21. I'm going to slide down here to 21 degrees of freedom, slide on over that row, and you will end up getting, if you looked it up in your t-table, 2.080. That would be our critical value. So our critical value is always going to be from a table, and that's where we're going to find this one. Please also note that if you go all the way down to the very bottom where it says infinity down here, there'll be a little spot, the very last row will say infinity. That is just your z-scores. Because z-scores is what you would get if you had a sample size of infinite size. So you can just use that for your z-scores. So what I want you guys to do is now, on your sheet, you should have this on your worksheet, go ahead and find what's the z-score for our 95% confidence interval. We all know that one, right? 95% confidence interval from our previous table before. We know that this z-score is 1.96. And you can confirm this at the very bottom row also, the infinity row, right, of your t-table. You'll see that there. But also, I want you now to find the t-scores for n is 2, 11, 61, and 127. So when you get 127, then your degrees of freedom here, we'll take a look. Degrees of freedom would be 127 minus 1, so it'd be 126. If you look at your table, your options are going to be 120, and the next one is like 500. So which one is 126 closer to, 120 or 500? And make that determination and find these scores. So go ahead and pause this. Actually, this is the end of this video. So go ahead and fill these out, look them up on your table, fill these out, and then when you're done with that, and download that table if you don't have it, and then again, find these, fill them out in your sheet, and then we'll go ahead and start the next video with the beginning of that part there. Okay, so actually maybe once you find these, maybe take a little short break, walk around for a couple minutes, get a drink and relax a bit, and then come back to it, after a short break. Okay, so we'll see you soon.